So let's take a look at some more benzene reactions. And the next kind of reaction we want to look at is still an electrophilic aromatic substitution, but let's switch to the Friedel-Crafts reactions which we have in our chapter 16 notes. So specifically looking at three reactions today, an alkylation with aluminium chloride, and then a more extensive alkylation with aluminium chloride, and then an alkynylation using the carbonyl derivative, as you can see in the third reaction here, this time using iron bromide as a Lewis acid catalyst. So let's try the first one, and that's the alkylation with the chloroalkane and using aluminium chloride as the catalyst. So as we've seen before, the first step really is to make sure that we enhance the electrophilic nature of that electrophile by making it electron hungry. So we have a chlorine, which is using its pair of electrons to form a bond to the Lewis acid catalyst. And then the complex which is formed leaves a positive charge on the chlorine, being more electronegative than carbon or the aluminium. It's not going to stand for that, so it's going to break the chlorine to carbon bond and take the electrons with it. So we should form, as we saw before, an ion pair for these species. That carbocation derivative still bonded to the aluminium tetrachloride using that ion pair for stability. So as the benzene ring comes in as a nucleophile, a relatively modest nucleophile, but we've got a much stronger electrophile because of its need for electrons because of that formally charged carbon. So the benzene ring can use an electron pair from the pi electron system to make a new chemical bond, nucleophile to electrophile. So we attach the alkyl group to the ring. And then of course that instability with the loss of aromatic nature is stabilized because of the many resonance forms we can draw as the electrons move around the ring, moving that positive charge around the ring. So everybody is carrying that heavy burden, and with the more resonance structures we can draw, the more stable the intermediate becomes. So we get 1, 2, 3 resonance structures in all. Now we want to return the molecule to an aromatic nature by the end. So we get rid of that hydrogen, which is on the carbon where the alkyl group appears. So we need that chlorine to aluminium bond to break. And we use the electrons to pick up the hydrogen, pick up the proton. So the chlorine is detaching, taking the electrons with it to use to make a new chlorine to hydrogen bond. And as that happens, those electrons in the bond are going to swing round and plug in that electron gap with the empty atomic orbital on the carbon here. So we'll produce a final product, that aromatic product, which has now been substituted with the ethyl group, and we restore the aluminium chloride and get a little bit of hydrogen chloride as byproduct. So let's take a look at the next reaction. So we begin again with an attempt to try and make a better electrophile than we already have. So the chloroalkane attacks the aluminium chloride, and we form this molecular complex which puts a formal charge on the chlorine. And of course the chlorine isn't going to stand for that, so it pulls the electrons to sever the bond to the carbon, But as that happens, next door on the adjacent carbon, the carbon to hydrogen bond breaks and the electrons hop over, taking the hydrogen with it, so that we can form a more substituted carbocation. So instead of a primary carbocation as we had in the last example, we're going to actually form a secondary carbocation in the ion pair. And of course this is what we've called in the past as a 1,2 shift. So this is something that often happens with the Friedel-Crafts reaction. If the alkyl chain being attached is long enough and a more substituted, more stable carbocation could be formed, then it means we're going to get some rearrangement through this 1,2 shift, and it's going to change the identity of the product compared to what we originally expected. This substituted structure, instead of a straight 1, 2, 3 carbons added onto the benzene ring. So it's this improved carbocation which is then attacked by the benzene. As it attaches to the ring, we lose the aromatic nature of our intermediate, but that's okay because the electrons can swing around those atomic orbitals above and below the ring, and we can produce these resonance structures. Again, positive charge on the empty atomic orbital here, so the electrons in the pi bond swing around and we produce a third and final resonance structure. Now to finish off the reaction, that chlorine, which we initially added on to the aluminium chloride, is going to break away, taking the electrons in that chemical bond with it. So it can form a little bit of hydrogen chloride, and the electrons in that carbon to hydrogen bond, now that the hydrogen has departed, they swing around and they plug in the gap to complete the aromatic nature of our final product. So this rearranged alkyl substitution with hydrogen chloride produced and some aluminium chloride returned as a catalytic amount. So before we go to the last reaction, there's a couple of things that we have to think about because of the way this reaction has rearranged. So in general, when we're talking about Friedel-Crafts reactions, please be aware that we might get 1,2 shifts to form a more stable carbocation, and that means we might not get the product that we actually desire. The Friedel-Crafts reactions are also notorious for being slower or even not happening at all if we've got some kind of electron withdrawing group already on the benzene ring, because that deactivates the ring and will slow down reaction or completely halt it. And also those Friedel-Crafts reactions can often keep going when we add an alkyl group onto the molecule, because alkyl groups are electron donating through the inductive effect and will actually activate the ring. So it's possible you could get that alkylation to happen a second or even a third time, and that might not be what you're after. So an alternative to the Friedel-Crafts alkylation is the Friedel-Crafts alkylation reaction, which is putting a carbonyl substituted group onto the aromatic ring. Again, we need to start with an improved electrophile by making it electron hungry. So again, the halogen, which is on, attacks the Lewis acid catalyst, and we form this molecular complex briefly. Of course, the bromine with a positive charge isn't going to stand for that when it's the more electronegative element. It's drawing electrons towards itself. So it will break the nearby bromine to carbon bond and produce this carbonyl cation, which was seen before as resonance stabilized because the oxygen can donate a pair of electrons and make an oxygen to carbon triple bond, the psyllium ion, as we've talked about in the past. So the cation that's formed is resonance stabilized before the reaction with benzene starts. Moving on to the benzene itself. So again, using its pi electrons to form a new bond to that carbonyl ion. So we get attachment to the ring and briefly lose that aromatic nature. But of course we've got resonance stabilization as the electrons move around the ring, filling in that electron gap at those empty atomic orbitals each time. Electrons moving a second time and then a third time as we produce free resonance structures. And to finish off the reaction as normal, that bromine we attached to the Lewis acid catalyst will break off, taking the bonding electrons with it as it picks up that hydrogen. And as that bond breaks, the electrons swing round to plug in that electron gap and reproduce aromatic nature to a final product. So, whichever way we do it, there's a potential for problems. We want the first reaction here to produce this nice alkylated chain on the benzene ring. If we were to try that, a major product would actually be the rearranged product through a 1,2 shift. We could try using the carbonyl compound, which would avoid the 1,2 shift because the initial cation is stabilized. But with this carbonyl group, it's maybe not what we originally had in mind for the molecule. So what's the ultimate solution? Well, what we can do is use that last method, the Friedel-Crafts alkylation. And then with hydrogen in a hydrogen atmosphere, maybe about 2 or 3 atmospheres of hydrogen, and palladium on charcoal as a cheap catalyst, we can actually reduce that carbonyl group to give us the alkyl chain that we wanted. So a multi-step synthesis is probably the answer whenever we want alkylation of a benzene ring.